Hey everybody, so today we are talking with Dr. Fran Bagenal. Dr. Bagenal is a Professor Emeritus at CU Boulder and has been involved in a number of planetary science missions from Juno to New Horizons, Cassini, Galileo, Voyager. She's sat on or chaired a growing number of NASA assessment groups, advisory councils, review boards, and has received numerous awards for excellence in research and teaching. Dr. Bagenal is also a longtime proponent of a mission to Pluto, and her work as co-investigator for the New Horizons mission makes her a prime resource for understanding the environment of the Kuiper Belt and beyond. And her enthusiasm for teaching and lecturing is legendary, and she may be the only CU APS faculty with an IMDB page. So we are thrilled to have Dr. Fran Bagenal here with us today. Thanks for joining us, Dr. Bagenal.
It's a pleasure. Great fun.
We're happy.
Hopefully we'll be back in person in Fiske before too long.
Fingers crossed. All right, so let's kind of jump right in. So we're here today to talk about New Horizons and the outer solar system and some of the cool stuff that's happening out there. So I figured we kind of start at the beginning. Talking about New Horizons, it was accepted by NASA in 2001, launched in 2006. But you and some others had been pushing for a mission to Pluto for a while before then, is that right?
Yeah, it all really started back in 1989 when I just started at CU. And we had the Voyager flyby of Triton at Neptune. And this got everybody excited about Triton is a captured object at Neptune and thought to be a Kuiper Belt object. But of course, back then, we didn't know about the Kuiper Belt. All we knew is that Triton was probably captured. It was going the wrong way around Neptune. And that it kind of the same size as Pluto. So there was some interest, what do we do now after Voyager? Help, panic, where do we go? What do we do? And Alan Stern came to me, he was a graduate student at the time, and said, let's go to Pluto. And I thought, who cares about Pluto? Pilly little object, who cares? Because I deal with big objects like Jupiter, Saturn, all these things. And so he persuaded me, though, that it would be an interesting place to go, because in some ways and we'll come back to this, I'm sure, you can think of Pluto as a very large comet, if you like, in that it likely hasn't. We know it has an atmosphere. We knew back then it had an atmosphere, and the atmosphere is probably escaping. So you can think of it a bit like a comet. So that's what got me interested in it scientifically. But what's really interesting is this. When we started 1989, there was no Kuiper Belt, just Pluto. And then in 92, they discovered the first Kuiper Belt object. And then many, many more that were discovered quite quickly using Earth-based telescopes, looking out there and seeing these little dots. And we realized that there was another zone out there in the solar system that had not been explored. And this became very important in terms of solar system formation. So the key to us successfully getting NASA interested was very much the idea that Pluto was one of the Kuiper Belt. And so before we discovered the Kuiper Belt in the mid-90s, we were just wasting our time. People were like, who cares, who cares? So there was a combination of what to do next and scientific motivation for going, but also the discovery of the Kuiper Belt to be.
Yeah, that's very cool. And I guess that kind of answers my next question is, what was it about a mission to Pluto that everybody thought was so imperative? And, obviously discovering this whole new area of our solar system is a big deal. Right. And I know things like timing also have a lot to do with it. You had to get a mission off the ground at a certain point so it could get to Pluto in a reasonable amount of time.
So there's a little bit, I have to be honest with you here. Yes, we need to do a flyby of Jupiter, but that comes around every 13 months. It's fairly often. It's not a big deal. We were concerned the atmosphere would collapse. At least that was the game we were playing. It wasn't clear the atmosphere really would collapse, but it was clear that if we said, it might collapse, the atmosphere might collapse, we have to go, we have to be there. That sort of added that urgency. that told us we had to go soon. And so that helped. Of course, current ideas are that, no, it changes, but probably not completely collapse.
So that was part of the push for the mission, is that idea that maybe it would, or it was, and that kind of got people on board to say, yeah, okay.
You know, there was good reason to believe that it could collapse.
Sure, right, collapse. Of course,
and
of
we
course.
don't know, and therefore we need to go find out. Right.
Well, you know, on the subject of you know, what we kind of learn when we visit a planet, such as going to Pluto, you know, your work deals primarily with magnetic fields and plasma, but I've always been taught that Pluto doesn't have a magnetic field and that plasmas are very hot. And I'm guessing that there are some misconceptions here. Could you give us an idea?
No. So indeed, I've said from day one that Pluto doesn't have a magnetic field. It's way too small, much smaller than the moon. The moon doesn't have a magnetic field. Though my colleague, Ralph McNutt, who was a grad student with me at MIT back in the Voyager days, he always said, well, you never know, could do. And so I sort of roped him into the team, and he ended up heading one of the instruments on the New Horizons, which is great, the charged particle instrument. So we always knew that the interaction would be mostly solar wind interaction with the atmosphere of Pluto. And indeed, that is what we found. We had predictions that it would be a very large volume of interaction, because we thought the atmosphere was escaping, and that because the solar wind is quite tenuous and the magnetic field of the sun is very weak out at Pluto's distance, that we thought it would be a very large interaction region. And our predictions were, until we arrived there and found that it was actually really quite small and compressed. And that also fed into the observations that were made about the atmosphere. And so you can, if you look at the atmosphere, you see these layers of aerosols. But in fact, above that, it's really quite, it is not as expanded as you would expect with simple ideas, simple models. Yes, it absorbs the UV light of the sun out there, and there isn't a whole lot of it, but it's a fairly, any UV light adds a lot of heat to the atmosphere, and we expected the atmosphere to be puffed up. But it wasn't puffed up, which was a big surprise, and we didn't know why. And then we learned that these aerosols combined with maybe water, maybe some other sort of molecule. We don't actually know which molecule it is, but probably some combination of oxygen, hydrogen, carbon, nitrogen, you know, the main elements, ends up radiating heat out. And so in many ways, Pluto has the opposite of a greenhouse gas atmosphere. It has a radiating atmosphere, not an absorbing atmosphere. And so makes it cold. Now, if we knew what that magic chemical was, maybe we need to put it in our atmosphere to cool our atmosphere down here on the Earth. You know, one might use it for global warming, but I mean, when you're partly joking, you know, we need to think about these things. But for Pluto, what it means is the atmosphere is much less puffed out and much more compressed than we thought. And so the interaction is indeed sort of cometary, but maybe more like a Mars interaction with the atmosphere, and a Venus interaction with an atmosphere less than a comet-like interaction with the solar wind. Yeah. So the solar wind goes by and it ionizes the outer layers of the atmosphere and strips it away and carries it downstream.
So just to be clear, the atmosphere of Pluto is actively getting rid of heat rather than containing it. That's the takeaway, is that it's and that's unusual. That's not usually what we expect from planetary atmospheres.
So there's very little of the greenhouse gases like CO2, CO, those are the famous greenhouse gases, right? A lot of nitrogen. There's these aerosols that you can see in the atmosphere that tends to be this sort of hydrocarbons that are raining out. And those are the materials, then they rain out of the atmosphere that cover the surface of Pluto, make it look brownie colored. So the very old, geologically old surfaces are covered with this brown gunky stuff, which is in fact coming out of the atmosphere. So you're removing the material some of the material that could be greenhouse gases, and the actual gases in the atmosphere do tend to be radiating rather than absorbing.
And those layers of aerosol, is that what we're seeing in your background behind you, those stripes? If for anyone watching this on YouTube versus just listening, Dr. Bagenal has this zoom background of the atmosphere of Pluto, and that's what those lines are.
Right. This is my favorite picture that was taken as the spacecraft left, and I'm going to step aside and you can see the whole picture.
Oh, okay. Great.
So what you're seeing here is ice geology. The rocks are in fact water ice. You're seeing a sort of flattish area, which is nitrogen ice glaciers. And then in the deep distance, you are seeing the atmosphere, the hydrocarbons that form aerosols, the haze in the back. And I just think this looks so planetary, right? It's so much like all the features of planets. And so I hold this up in public talks and say, looks like a planet, doesn't it?
Well, it certainly does feel much more familiar than I think a lot of people might expect when we talk about Pluto. You see stuff that kind of looks earthly and you're like, wow, it does. That feels very real. And it's very striking to look at. So talking about, these unexpected kind of phenomenon that we observed when we got to Pluto, there's probably tons of surprises when you start looking through the data from New Horizons. Was one of them your favorite, or one that you think was most surprising, one fact that we kind of learned from this mission?
I think the glacier and this thing here, the glacier here, you're seeing nitrogen ice convecting, turning over. Now, it's geological timescale, so it's 500,000 years to turn over. It's not rapid. On the other hand, it turns out that nitrogen ice is less viscous or more runny, flows more easily than water ice. And so you can have these glaciers and this convection turning over of nitrogen ice driven quite easily with very little heat from below. And then that leads to a lot of geological activity, which was, I think, a big surprise. Yeah.
So when you say the fluidity of ice, you just described ice as being viscous or not viscous. How does that work? Because when I think of ice, I think of a solid, right? That's the solid phase of water, for example. So what does that mean, the fluidity of ice?
There's two ways of thinking of it. One is just to think about glaciers, which move fairly slowly. I mean, glacial comes from the idea of a glacier moving slowly, and the ice moves. But if you go and you look online and find Balog's movies of the glacier, it's really amazing. He has these time-lapse movies of the Earth's glaciers and pointing out their retreat, but you can see the flow. A better way of thinking of it is to use what I do when I teach this in planetary classes, is to take silly putty. And if you take silly putty and you warm it a bit in your hand, and you make a nice ball, and you put it down on a table and wait, you will see it flow out, okay? And that is low viscosity flow, right? And if you warm it up more, it'll flow quicker, right? You could say the same about jam or take your favorite food that slops around, I don't know, Jello or what are other foods that flow? I guess you could take honey, right?
The classic example of syrup, maybe.
Syrup is the other one, right? If you have it very, very cold, it moves very slowly, and then you warm it up a little bit, and whoa, it flows quite quickly. So the same is true for ices. They are not, and indeed rocks flow, right? When they warm up inside the Earth, they flow. So most of these things that you think of as being solid, if you leave them long enough, they will begin to flow. Yeah.
And of course, New Horizons didn't just stop at Pluto. It kept going. We had a rendezvous with Arrokoth, another small Kuiper Belt object, and New Horizons is still going out. So do we have any idea of where New Horizons is headed next?
Well, there is hope that we could do a flyby of another Kuiper Belt object, but you have to, it's tough out there. So to go from Pluto to Arrokoth, if you hold up your finger and you think from your eye to your finger, that angle is about 2 degrees, okay? Maybe it's 1 degree, maybe 2 fingers are 2 degrees. On that order, depending how long your arm is, of course. But the point is, we had very little maneuverability, about 2 degrees, when we were at Pluto to get to Arrokoth. Because of the fuel, if you want to change direction, you have to burn an engine on the spacecraft. And we didn't have a lot of fuel. We have even less now because we've gone past Arrokoth. And so there's very little fuel. So that means that you've got to look for an object that's right in that direction. And the chances of that are extremely slim. We're using Hubble Space Telescope and other ground-based telescopes to look and see if we can see anything out there. But I think the chances are slim. And so the idea is for the extended mission, the continuous, if we're able to keep continuing, is to do a variety of things. That is, look at Kuiper Belt objects from different directions to try and learn a little bit about them from there. I'll come back to that in a second. Another is to look at the background, Lyman alpha, of the far astronomical observations that you might want to take of the UV light that comes from the stars outside. We will measure the solar wind using the solar wind instrument, the SWAP instrument. Variety of tools of things that we can do, looking at different Kuiper Belt objects and looking at the solar wind, watching it slow down as we move out through the heliosphere, the sphere of influence of the sun, because the effect of the material outside coming in and slowing down the solar wind. So there are a variety of things that we're doing, but I think the most exciting one to me is actually something that came out been demonstrated in the past few weeks, is this citizen science experiment that is to look at Kuiper Belt objects from the viewpoint of not Earth looking out, but New Horizons, which is out there looking sideways, if you like. So a slightly different viewpoint. And so when you look at things from different viewpoints, you get to see the location, you get to work out where it is. It's called a parallax effect. And it's been used for centuries for measuring the distance to stars. And we can use the difference in viewpoint from Earth and from New Horizons to sort of work out where these objects are. It's a really cool experiment. And we've been engaging with citizen scientists to look for objects like that and do this experiment. And you can go online and see it. But maybe the coolest thing is that Brian May from the band Queen is involved. He's an astronomer and keen in these things. And of course, he's written music to go with it. And you can go online and see it. It's kind of cool.
That's very cool. I did just see an article where they had used that parallax technique to look at Alpha Proxima Centauri, the closest star.
Cool.
And they had been doing updated measurements on how far it is to our closest star, thanks to
our closest star. Yeah, right. Exactly. Really cool.
Yeah. And you mentioned that it's getting kind of low on fuel. Do we know how much longer New Horizons is going to be out cruising?
Well, you know, it's not moving as fast as Voyager because it didn't get in as close and get as big a gravity kick. So it'll never catch up with Voyager and certainly won't overtake it. So we think that it's out at about 45 times the distance between the Earth and the Sun. And it'll head out to about 60. So, you know, it's probably, I don't know, 5 to 10 years. I don't know the exact number. And it sort of depends a bit on how much fuel you use and how cold it gets and do you turn off some instruments and so on and so forth, and how much backup we can rely on, and so on and so forth. But it won't get out of the Kuiper belt. It'll get to the edge of the Kuiper belt. And so one of the instruments, the student dust counter, built here at the University of Colorado by students, the best instrument delivered first, instrument delivered on time, on schedule, and operated by students ever since. But that instrument measures the dust that is generated when objects bump into each other. And they don't bump into each other very often, obviously, because there isn't a whole lot. Space really is very empty out there. But they generate a little bit of dust that over a period of about 1 million years begins to come in towards the sun. It sort of, it interacts with the sunlight, and it slows down and comes in. But the point is, when you get beyond the Kuiper belt, does the dust disappear? So one indication would be with the student dust counter, measured a fairly constant amount of dust, and it's only a few hits per week. This is not a huge flux of dust, right? But we can measure it over years and years and years. Go out, and that will tell us if it suddenly drops off, the flux of dust stops. Then that tells us that the interaction between these objects, there isn't enough more objects out there to be generating the dust.
So even way out at the edges, we're still learning stuff.
We're still learning stuff, right?
Yeah.
Yeah.
As far as when you say you run out of fuel, we're talking about the ability to provide thrust to the spacecraft, right, and change course. What about looking in different directions? What about rotating and, you know, checking out something over there or over there, but you're still on the same path?
Right.
What does that look like?
Actually, 3 kinds of fuel. There's the fuel that we use for power, radioactive thermoelectric generators, so using nuclear fuel to generate heat that's converted into electricity. And so that, because it's produced by radioactive decay, it has something like a 76-year half-life, so it gets less and less and less and less and less time. And so we will run out of nuclear fuel that produces energy to power the spacecraft and heat it up and do all the electronics and the communication to Earth. The second kind of fuel is that powering, and the engines, against common ideas that the engines are always running. No, you only turn on the engines when you want to change direction or speed up or slow down. So most of the time you're just drifting due to the laws of gravity. You're just moving in the gravitational field of the sun or whatever planets you may be slightly close to. The third kind is indeed what you pointed out, this issue of orienting the spacecraft. And if you want to change the orientation of the spacecraft, you have a little jet. So if you wanted to tilt it this way, you'd have to push here or push here, right, to make it go like that. And so what you do is you have a jet. So to tilt this, oops, that's not working very well. I put it right in front of my face, it'll work, there we go. To make it go this way, right? So you want this to go over here, then what you do is you fire an engine that goes this way and it pushes it that way. Yeah. But we will run out of fuel, and that is a little bit of hydrazine on which is, you know, which mixes with oxygen, and you puff it out and it will work, but only a finite amount in the tanks. Yeah.
So since we have learned so much from just this one flyby of Pluto and, you know, out in the Kuiper belt, is there maybe another Pluto mission that's, pardon the pun, but like on the horizon?
There is a mission, and there's a group of people who are pushing for that. And that would be interesting and a good thing to do. It would be challenging, because if you want to go into orbit around Pluto, you have to not only go all the way out there, but you also have to slow down to go into orbit, and that is tough. So you have to carry a fair amount of fuel to do that. of some kind. I don't know. The other option is to say, well, why not go to one of the other Kuiper Belt objects and learn about that? Which is more important, to go back to Pluto or to go to a different Kuiper Belt object? For me personally, I think I would go with a different Kuiper Belt object. You know, Alan Stern is pushing to go back, you know, with some of his members of his team to Pluto. I think go elsewhere and go look at a different Kuiper Belt. I also really want to go look at Triton, which is the captured Kuiper Belt object in orbit around Neptune. Uranus and Neptune have only been explored by Voyager flying by, the only spacecraft that have gone close to them. And I think it would be very interesting to go to either Uranus or Neptune and explore those planets and find out what's going on. But their outer solar system is tough. It is difficult. So it takes time.
I know that's kind of a big debate that I've had with some of my teammates, is they think we should really go back and study this thing that we already visited because we know it's really cool and we know that it has a lot of potential. But then on the flip side, there's all this other stuff that we haven't been to yet that, I mean, personally, yeah. I agree. I think it's worth going and checking these out too.
So I'll just pick on Mars for a second. Tara, I hope you don't mind, but you know, we've been going back to Mars again and again and again and again. And yes, I know it's interesting, exciting, but we've done it. And we need to go somewhere that's a lot tougher. Venus, next door planet, right? Greenhouse gas that's gone absolutely crazy. An atmosphere that's like out of this world, right? Hot and an Earth that's gone extreme greenhouse global warming. I think we really need to go back and understand Venus. You know, get under the clouds, look around, go back up, cool off, go back down, have a look around, go back up, cool off, or whatever. I mean, I think there's 100 different things we could do at Venus that would be really interesting. So, and that's just a neighborhood. And it doesn't have a magnetic field. So I'm not pushing it for my own professional purposes.
As far as, so this is kind of a personal question, as far as the role of space science, do you think, I guess both of you two, what's your thought on, should we try to go like wide and get as much information on as many different objects or things as possible? Or is there utility to going deep and saying, you know, we've been to Mars 1,000,000 times, but if we go 1,000,000 more times, then we'll learn that much more about Mars specifically. How do we divvy that up in an era where space travel is still fairly new in the grand scheme of things, and it's super expensive and it takes tons of time to put things together? How do we divvy all of those things up?
So that's what the Decadal Survey is for. And we've just started one. The National Academy of Sciences, funded by NASA, but supposedly is independent, is being just cranked up and started for planetary science. We do it obviously every decade. It's also true for heliophysics and for astrophysics and for earth sciences. But for planetary science, we've done it before, a couple of times before. We can do it again right now. And people write their white papers. I think we should do this. I think we should do that. I think we should do the other. And then there will be panels that focus on, you know, the giant planets or the terrestrial planets or whatever, or maybe astrobiology, maybe dynamics. So I don't really know what the panels are going to be, but they have topics that are covered, some panels. And then the main core of a dozen or so senior scientists who will be then evaluating this and writing a report that says, these are the priorities of what we should be doing. And so this sort of process of evaluating, what do we do next? Do we go in focus deep on something where we've got a big question we want to answer? How do you balance that against, we've never been to a blah, blah, blah. Let's go to a blah, blah, blah and find out how blah, blah, blahs work or whatever it is. You know, it could be, say, an asteroid that's that comes in close, or you know, a Kuiper Belt object that has this kind of characteristics. Or you might say, what about all of the captured little moons of Jupiter? I have reason to believe that they're very important for dynamics. I don't know, I'm just making this up, right? And so you could have a focused reason to go and explore a different region for a different purpose. Yeah.
Got it. That clears things up. Thank you. Yeah. So before we kind of started talking about, well, about, the kind of overall, how do we decide where to go? We just about left off on that it takes a very long time to get to the outer solar system as far as spacecraft goes. And this might be an ignorant question, I'm not sure, but I'm going to ask it anyways, which is when we talk about sending spacecraft to such distant destinations, we're talking about literal decades of time, right? Or at least in New Horizons, it was 9 years, right? 2006 to 2015. How do scientists cope with the journey? Is there significant research that can be done with information on the way? Or is it one of those things where you just kind of let it go and, launch it, and then you just remember it 9 years later and say, okay, we're here, let's start. And in the meantime, you were doing something totally different.
So of course, there's a team of engineers who are keeping an eye on the spacecraft, sending it signals occasionally, listening to it. There's some communication going on, though we did do a lot of hibernation on New Horizons to try and cut down cost and keep it simple. The scientists are doing a combination of things. Some of them are still working on other projects. Maybe a lot of the people on New Horizons also worked on, say, Cassini, or they had Mars missions they were interested in, or I was getting ready with Juno to get ready to go to Jupiter and things like that. So they got other projects that they're working on, or they may be analyzing old data sets. I actually worked with a couple of students to reanalyze all the Voyager data at Jupiter again. And we published a paper in 2017 on data that was taken in 1979. I mean, you reanalyze it regularly. Modeling, people are doing modeling, and then particularly with Pluto, there was a lot of people who were using Hubble and ground-based telescopes to look and give context. What can we learn from the Earth to try and understand bits about Pluto before we get there? So there was this big campaign to do these occultations of stars going behind Pluto and measuring the atmosphere, and particularly Arrokoth, to try and get the shape of Arrokoth before we arrived there with New Horizons. So there are these other campaigns using other techniques and tools that are going on at the same time, sometimes focused on the target that you're going to go visit and learn more, so you're ready when you get there. Hone your questions, your hypotheses about why it is the way it is. Or you're working on other targets that are maybe related, So say you work on a Pluto mission, you might go back and review all the literature on Triton and say, are there some pieces of information about Triton that will be useful to keep in mind when we get to Pluto and stuff like that.
Got it. So as far as, I assume that's one of, I don't know, would you call that a challenge? The distance, the time, or is that just like built in? Yeah, that's something that is tough.
I want the now. I want to get the now.
Right. As far as, so, that's a huge challenge, right? And that's not easy to overcome because it's just traveling through space, and
right.
We kind of have to obey some rules when we do that, set by nature. What about other challenges with going to such distant places, aside from the amount of time it takes to get there, and perhaps the amount of fuel that we need to kind of plan for, and all of those travel challenges? What other things that are maybe not so obvious do scientists and engineers have to think about and consider when we talk about sending spacecraft to the edge of the solar system?
So one thing is communication. We carry a radio dish and send the signals back to Earth, and we use the Deep Space Network, which is 3 big telescopes around the Earth. Now, there are actually not just 3 big telescopes. There are 3 main places, one in Australia, one in the US, one in Madrid in Spain. And so the obvious point, if I might, yes, here we go. If you think about it and you have the Earth, I'll have my little smiley face, rotating around, if you're trying to communicate, if you have 3 places around with antennas, you can be as one observes for a while, then hands over to the other to observe for a while, and so on. And so you can observe and communicate with a satellite that's deep out in space by receiving the radio and taking it in turns as the Earth rotates around. Now, we have quite large dishes. Each of those has a 70 meter, which is about 210 feet across radio dish, and you have to precisely move it around to get the signal.
I remember that was something that we considered with the Apollo missions, is that, you know, we never wanted to be out of touch with the astronauts that were on the moon, because you can't very easily just look through the Earth for that signal. And so it was a similar thing where you always had one line of communication at least over to the moon.
And I think there's a cool movie about the Australian radio place that was receiving at the critical moment, getting the Apollo signals coming back. I can't remember the name of the movie, but it's a cool movie to go watch if you're a space nut. But if you think about it, it costs a lot of money to send the spacecraft out there, and it takes a lot of power to communicate with radio signals and a fairly big dish. What about making the ears on the ground bigger, right? If you could make those dishes not just 170 meter, but 5 or 6 of them that are together, that you array into and all listen at the same time, you could listen to much weaker signals. You might be able to send more information. Now, the amount of information we sent was very limited. It was, you know, it would take the best part of a day to send one image, and you would want to send a lot more than that. So I'm sort of frustrated that the ears on the ground, although you think these antennas are expensive, they're a heck of a lot cheaper than the spacecraft. You know, we could build much bigger ears on the ground. And I don't really know why we don't, to be really quite honest with you. We really should. It would be worthwhile investment. It's partly a problem because it would really need to be a international collaboration to try and make this work better. But I think we really should build that up.
I imagine that kind of investment, if we were, you know, if the scientific community were to come together and say, all right, we're gonna make these ears bigger, that could be used for, it's not just a one mission thing, right? That's now something that you can use for you know, missions, you know, as far as the eye can see.
Sure, all missions. So if you go on the internet and you go look at the Deep Space Network, you can actually pull up a page that shows you which of these 3 stations are listening to what spacecraft. And it's kind of cool to go watch those signals. I mean, it's a cartoon that just shows you, you know, which one is operating. And they have a dish and the name of the spacecraft and a wiggly line coming in. And it just indicates that they're listening. And it's kind of fun with your own spacecraft. Wow, they're listening to Juno right now. Wow, they're listening to Voyager. Voyager that sent the signal 17 hours ago. They're finally getting it in California.
Well, I think that's a cool way to kind of loop in, you know, the civilian community of non-scientists to kind of say, yeah, this is real. It's an easy way to kind of really be in touch with how this is actually happening. So yeah, that is really cool. We'll try and link that somewhere in the episode somehow. That's really neat.
And one of the things that we talked about as a challenge was carrying enough fuel to get all the way out there. And you talked about New Horizons being nuclear powered. But we see a lot of spacecraft that have these humongous solar panels and are solar powered. So where's kind of the line where we draw that, okay, solar power is only going to get us so far? How far will it get us?
Right. So we now know with Juno that you can use solar power at Jupiter. And that was there were skeptics. And the reason was that the US stopped making the nuclear fuel that we needed. You have to make it in a nuclear reactor. And the idea was that we didn't really need it. We were able to get some from Russia. They were willing to sell it. And sort of cobbled it together. Now the US is starting to make more, but they're making a tiny amount per year. So this is a really tough thing, is the nuclear power. Now, the reality is that you're not, just because, you know, spreading out of sunlight, and you think of a sphere of the sunlight coming out from the sun, and as you move further and further away, that area increases by distance squared, right? That area of the sphere. And so the flux per unit area decreases by 1/r squared. So as you move out, if you double the distance, the amount of flux from the sun goes down by a factor of 4, 2 squared, 4. You go out to 5, like Jupiter, it drops by a factor of 25, 5 squared. And you get out to Pluto, which is at 30 AU, then you're dropping it by a factor of 1,000. So, you know, you can't use solar power to power your spacecraft out of Pluto. Jupiter is about right now the cutoff point. Once we get more efficient solar arrays, and there's a big hope in the solar community, particularly people here living in Boulder who love solar power. I have solar panels just outside my window. You know, we want there to be more efficient, and the technologists are working on more efficiency of solar panels, making them lighter, making them more efficient. It's possible that we could fly large ones further, but we're not there yet. So power, and when I'm not talking fuel as in engine fuel to change the direction or orientation of the spacecraft, this is providing electricity to heat the spacecraft, to run the computers, to communicate with Earth with the radio antenna. Yeah, tough.
So kind of a related question, I guess, is, you know, that sunlight is spreading out and the solar wind is getting smaller and thinner and thinner. How far out does our sun's influence go? Does it go past the Kuiper belt? Does it keep going?
Great question. So I worked on the Voyager mission since I was a graduate student, and it was great fun to work Jupiter, Saturn, Uranus, Neptune. And then by Neptune, we get to 30 times the distance between the Earth and the sun. Okay, distance between the Earth and the sun is an astronomical unit known as an AU. So let's just use AU, right? So when I say AU, I mean distance between the Earth and the sun. So then you go beyond Neptune at 30 AU, and the Voyager spacecraft, Voyager 2, kept going out, and Voyager 1 kept going out. Voyager 1 was going a little faster because it went closer to Jupiter. So it just went whoosh, charging out, a little north of the ecliptic plane, the plane of the planets. Whereas Voyager 2 actually was going down a little bit south of the plane of the planets. Anyway, Voyager 1 was the first to break out of the bubble, the Earth's, the solar influence around it. And it's funny because the time between when it was past Neptune and when it arrived, and I'm trying to remember the year, but I think it was about 2014, 15, something like that. I can't remember exactly which teen of the decade it was. Voyager 1, we were like, everybody kept saying, well, 5 years time, within 5 years, we'll be there, we'll be there. And just keep us going, And didn't happen. And then finally, we went out into the interstellar medium at about 100 or so astronomical units, AU. And I think Voyager 1 is at 120. You can look this up on the internet. Just say, where is Voyager now? And you can get that number. Voyager 2, this past December, it's pretty clear that it went out last year. And so they're both now out in the interstellar medium. And we're getting a sense of the shape of how the star stuff, the materials from the distant stars, or nearby stars, I should say, but they're very distant relative to the edge of our solar system, their material is coming in. So neutral hydrogen, just atomic hydrogen coming in, becoming ionized by the sunlight, UV light from the sun, then makes ionized to make protons, and those are the things that mix with the solar wind and then get carried out. And that's why the solar wind slows down, because you're adding momentum, you're taking momentum, from the solar wind by ionizing interstellar medium material. So yeah, we're out the bubble now. But I always have to add this very quickly, because we have to remember that edge of the solar system is a little different. Yeah, we got the planets, and yes, we got the Kuiper belt. The Kuiper belt probably doesn't go a whole lot beyond, 50, maybe 80 AU. But then we've got other objects, and there's this big debate about planet X. Is it there? Is it not there? And we've got objects like Sedna and so on, with elliptical orbits that go quite a long way out. But much, 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 much further is the Oort cloud of the comets, which kicked out in the early formation of the solar system epoch. And they are much further, thousands of AU out there. So when you talk about the edge of the solar system, it depends what you're talking about, right? And so the sun's gravity still holds in those Oort cloud of comets. And sometimes those Oort cloud comets get perturbed and kicked by a passing star in, and we see them. They come in the inner solar system, light up, and we get to see these comets. So it depends on what aspect of the solar system you're talking about.
So as far as, I don't know, I can't do that math in my head, but the Oort cloud, I think I've heard it extends up to what, a quarter or halfway to the next nearest star. Like it marks maybe somewhere near a halfway point between the sun and Proxima Centauri. Oh, really? Okay, good. So we don't know for sure. But I guess I'm curious, I wonder if there are, because I don't know off the top of my head how massive the stars in that Alpha Centauri group are. I wonder if there is even like the slightest chance that maybe one of the Voyager spacecraft, at some point in time that is feasible, would encounter some, piece of material that is in the gravitational sphere of influence from another star that's not the sun. If you imagine kind of like two overlapping, Oort clouds, so to speak, if they are extending this far away from their stars. I'm just curious if that's,
okay, so
kind of cool.
You've got to think about scale here. And maybe the way to do it is to talk about light years and light minutes and light hours. So a light year is the distance that light travels in 1 year. And we know that light travels from the sun to the earth in 4 minutes. And the signal from New Horizons, that is out of 30 AU, when it was at Pluto, took 4.5 hours to get to us here on Earth. And that the Voyager signal from 120 AU takes 17 light hours, something like that. So now you have to compare that with 4.5 light years, okay? So the nearest star is a long, long, long way away. So maybe you guys, since you work at Fiske, and we have a model solar system at Fiske, I remember, and you guys have done this homework much more recently than I did, when you walk along that model solar system and you go from Fiske to the edge of campus, you're going from the sun and the earth out to Pluto. So Pluto is right out there near the engineering building, right? Now, I remember that we used to say the nearest star was like Canada somewhere, northern Canada, maybe even Alaska.
I think the one I remember was the Panama Canal.
The Panama Canal, right?
Yeah.
Okay, same sort of thing, right? A heck of a long way away, right?
And for
So
people listening, the sun is the size of a grapefruit in this
the
setup,
sun
right?
is
We're
the
talking
sun
about the size of a grapefruit.
in the Fiske model solar system. So it's quite useful to think about things. That's why the value of these model solar systems are so fantastic, because it gives you this sense of space. And so you can imagine that you walk to the edge of the solar system on campus, which is still, you know, a little bit of a walk. And then you think about how far you'd have to go to the next star. So the reason why I'm emphasizing this is I really, really don't think, you know, these spacecraft, I mean, they will keep going, but and yes, they might bump into a piece of junk in thousands of years. I haven't done the arithmetic to say if they keep moving when they get to that distance, but it is thousands and thousands of years. So, you know, the Star Trek with the Voyager spacecraft on, was it Voyager 6? I think it was found abandoned on some distant planet. No.
Well, and I remember, you know, so right now, actually, there is construction underway to kind of update that scale model solar system. And one of the things that they're adding to it is the location of the Voyager spacecraft, which right now, for any CU people listening, is basically at the doors of fulldome. So if you imagine that the sun is right in front of Fiske, the Voyager spacecraft will be placed at basically the doors of fulldome.
Well, near where the buffalo is, right?
Exactly. Yep.
Right.
And so, yeah, I guess, you know, in retrospect, that was kind of a silly thought. It was, wow, I wonder if we'll ever, you know, get in touch with, because no, that's so close. You're still talking the same campus, less than a mile away, and the nearest star is the Panama Canal. So,
you know, this is very human. My sister asked me last week. She had a picture of some beautiful nebula and said, just how far away is it? You know, will we ever go there or something like that? And so I found a way to describe to her, it's really a long way away.
So let's talk, we always like to kind of ask some of these, you know, kind of personal questions about you as Dr. Fran Bagenal. My first question in this category is, what advice do you have for a person who really wants to study the outer solar system and work on spacecraft missions? Imagine there's some young listener out there saying, man, this sounds like exactly what I want to do. What would you tell that person? How can they get to kind of do what you're doing?
Number one, stick with your math. Do your math homework. Just do your math homework. It's really important. And I, by the way, would justify the entire NASA budget on encouraging kids to do the math homework. Benefits are huge. Even if you don't go into space research, doing your math homework is important. Number two, stick with your science and be curious and follow your curiosity. But if you want to do planetary science, then you have to stay kind of multidisciplinary, right? Because planetary science, you find you've got a bit of geology, a bit of geophysics, a bit of atmospheric science, a little bit of ice science, a little bit of gas, a little bit of plasma, a little bit of magnetic fields. You have to sort of be very willing to and open-minded to learn a little bit about all these different things, because they all tend to come together when you look at a planet that has a bit of everything. It's a very multidisciplinary science. If you really, really, really want to focus in, then, you know, go and work on the atomic physics of some atom, right? And you don't think about the other areas, or you know, maybe molecular biology is pretty sort of narrow these days. I don't know. Maybe I should. You know, you have to find what you're really interested in. Astrophysicists like to look at huge distances, fairly limited amount of information, but they leap about with fairly limited amounts of information and wild imaginations and come up with all sorts of cool stuff. Planetary scientists are a little bit more down to earth. They want some numbers, they want an image, they want some data to constrain their thinking, but you have to be multidisciplinary. Wouldn't you say, Tara? Wouldn't you say that's the case?
Yeah, absolutely. Planets are really complicated.
Yeah. Yeah.
Like you said, they have atmospheres and magnetic fields and geology, and even like I'm just specializing in geology, but there's ice geology and rock geology and surface atmosphere interactions that you have to worry about. And there's a lot going on.
Just look behind me here, right? Look at this stuff here. Lots of stuff. So those are the words of advice. You know, persistence, of course, with everything. But do your math, be curious, and keep your mind open to a range of science.
So I think that kind of leads nicely into this last question that we have prepared for you, which is, what is your story? Starting, you know, as a kid, from your IMDb bio, and I don't know if you wrote that or if someone else did. You have a bio on IMDb, and it talks about how, you know, as a young kid, you would stay up overnight watching, you know, the Apollo launches and what was it called? There was that weekly documentary series that was just kind of a general science. Horizons, that's the one.
BBC Horizon, yeah.
So how did that lead, you know, from your interest in science as a young child to what you're doing now? What did you study in your undergrad? How did that, you know, how did your path kind of move through? You know what I mean?
Yeah, so Apollo woke a lot of people, got a lot of people interested. Again, got you to do your math homework because you knew you were going to need it. And when I finished up at high school, and I studied math, physics, and chemistry at high school, because in England you have to specialize in the last couple of years. And I wanted to do, I was interested in geophysics, because this was the time when plate tectonics was just being sort of discovered and explored, and these ways of mapping out the ocean and looking at how the seafloor spreading, evidence for seafloor spreading and so on. There's a big debates about that. Really exciting. And then at the same time, there was missions to different planets. And I was very lucky, and I don't know whether it says this in my bio, but I was really lucky to meet Carl Sagan when I was 16. Went to a talk that he gave in Cambridge, in England. I lived nearby. My brother actually had met him and was hosting him, and I went to go hear his talk. And he was talking about Mariner 9 at Mars. So believe it or not, Tara, I started off with an interest in Mars. And because I have a reputation for being a little anti-Mars, but I don't mean it. It's just that I'm just a bit tired of it. So then I went on to university where I studied a combination. I didn't want to just do physics, but I wasn't ready to drop physics. So I did a combination of geophysics and physics together, hoping that I would either go into studies of Earth or studies of planets or something like that, right? And then I was really lucky. I decided I wanted to go abroad for a year and do a master's, because I really didn't know. In England, if you want to do a PhD, you have to know from day one, this is what I want to do. Or your advisor has to say, here's a problem, hand it to you, right? Do the problem that I hand you. And I wasn't sure what I wanted to do. So I went to MIT. I was lucky to get into MIT. And when I arrived, I took a bunch of classes. And they quite quickly said, why don't you stay and do a PhD? And I was, in the spring of that year, I went to it was a women in astronomy lunch or something like that, right? These things, it's amazing how you meet people and connections. And a woman there, senior woman on the faculty, said, oh, you need to go talk to the guys at the Center for Space Research. They're about to send a spacecraft out to Jupiter, the Voyager spacecraft. They got an instrument, does plasma measurements. And you've done some space physics, right? So my undergraduate thesis was on Earth space physics. So I went and knocked on the door, and they said, yeah, sure, we could do with some help. Rest is history. You know, I got involved on Voyager and, you know, went from Jupiter, Saturn, Uranus to Neptune. So very lucky.
That's a pretty awesome story. And I didn't know that in England that you started specializing so early, right? Because in the US, I mean, at least in any schools that I've ever heard of, your high school experience is pretty kind of cookie cutter, right? It's not, you don't really start saying, here's what I want to start studying and doing that in high school, other than some electives?
I think that the British system, it's a little less specialized than it was back then. And it could maybe go a little further, encourage people to be a little less narrow in their path, because you want to be able to move around. And I found when I was a postdoc working in London, undergraduates were really having a hard time. They would want to change their mind and the path wouldn't allow them to. Whereas the American system, you have a lot of flexibility. You can move around and change around, which is good. On the other hand, we don't have enough physics at high school, and we don't have enough people trained in physics at high schools. Only, I think, 30+% of high school, about 30% high school teachers have a physics degree, which is not what you want. You would want a much larger number who train the country in their physics. And so the net result, I've actually been doing a lot of demographic studies on this topic. What you end up with is the US doesn't produce enough PhDs in physics to supply the need to do the research that the US wants to do. So something like 40% of researchers are non-US, born outside the US, like me, and come to the US and stay here. Not all of them stay, but most of them stay. So LASP is 40% non-US PhDs. And that's because the US isn't producing enough, because they don't produce enough at high school and into college. So, you know, it's a problem.
Going back to what you said about, you know, just attending that lunch where you then kind of were informed about this project, and then that's kind of opened the door to a lot of stuff. And also kind of talking about, this is a really nice kind of loop in for a lot of things that you just mentioned, which was that in the US, you know, students, at least, you know, in my position, for example, are very fortunate to kind of be able to choose what we want to do and have that kind of liberty to explore different things, you know, without having to lock into something super early. Up until about my last semester of high school, I wanted to play music professionally. I'm a pianist and I do music theaters where my area is. And I had gotten into the school that I wanted to go to and things were kind of set. And then something just dawned on me and I said, no, I'd rather do science. And that's a whole different story. But the question I have for you is, in music, in the theater business, it's so based on connections, right? It's based on who you've talked to and who your friends are, and you know what kind of meetings you go to. In your experience, because that what your story about that lunch kind of made me think of this. In your experience, how is that in science? Is it a socially driven field, in the same way that music and theater are, or is it, you know, is there more opportunity for people that can just grind? What are your thoughts on that?
I think it's a lot more human connection than society would let you believe. I think a lot of people think you just do your homework, get the right answers, get great grades, and you go to the right school and you just keep grinding away. And no, that's not true. It is very much, are you asking good questions? Are you showing enthusiasm? Are you getting involved in projects? Are you particularly asking the right questions? And are you seeking out people who know and asking them those questions? Are you a fun person to be around? I mean, I'll be honest with you. I know people in our field, particularly way back when, I remember meeting a bunch of these when I was a grad student, and they were just not particularly pleasant people to be around. And they'd come into a meeting and go, you know, that sort of thing, right? And gee, surprise, surprise, I noticed 20 years later, no, they didn't have permanent jobs. You know, so actually being part of a team, working with a team, particularly in space research, you need to be part of a team, work with people, and be someone who's got a sense of humor, who's prepared to have a laugh and be friendly, and you know, not be a jerk. I guess that's an allowed word in podcasts.
I would say so. Yeah. Well, I guess it makes sense, you know, because we're talking about big groups of people that are working together in teams, and that is a very socially driven experience. If everyone gets along and feels comfortable kind of, talking and expressing their ideas and thoughts in a space without fear of someone like getting on them for whatever reason. It makes sense that those people that would be kind of.
So there's always been this joke about, the guys getting a job in the restroom or in the changing locker or whatever the phrase is used, right? And maybe that wasn't a modern concept, but when I was a student, everybody would talk about, the guys getting the job by, chatting with another guy, maybe in a social environment, male only social environment. I actually got my first postdoc in the ladies' room at a conference from Margie Kivelson, and we both like coffee, and we had to go to the loo, have a pee, and we were washing our hands afterwards, and she said, "Oh, where are you going to go?" I said, "Well, I'm thinking of going back to England." This was in America. We were at a conference in America, and she said, "Oh, they always say that. You'll be back." And she went and sat down next to a British guy, David Southwood, at Imperial College. And at the next break, he comes up to me and said, "How would you like a postdoc at Imperial College in London?" There you are.
And there it is. That's awesome. Very cool.
Especially like that because people so often think of scientists as being really stuffy and nose in the books and not very antisocial, but it actually takes a lot of social skill to excel in the sciences.
Yeah, I agree. And giving good talks, communicating well, it's increasingly, and I'm very glad to see that education public outreach is a major part of missions now, with a lot of citizen science, a lot of outreach, a lot of discussions, and I think that's great. Yeah.
My sister studies environmental science at the University of Denver, and she had to watch a film that's based off of a book. I can't remember what it's called. I think it's called Merchants of Doubt, and it's about climate change. And it's about how very charismatic, very believable people are kind of the driving force to this large-scale denial of human-caused climate change and its implications. And my sister and I were talking about how it's kind of tough because part of me thinks, well, if the atmospheric scientists that kind of in the environmental scientists that are the ones delivering this information to us as a whole population could somehow, not to blame it on them at all, but could somehow do it in the same charismatic way that a lot of these, because this film tells the story of how huge oil corporations are paying these super believable people, to say stuff that is, simply, it's just scripted, right? It's just, well, say this thing so that our industry remains unaffected by the fact that, climate change is real, etc. I wonder.
Yeah, we need Attenborough. We need to multiply him by a factor of.
Yeah, right.
Yeah,
right.
And others. I mean, there are scientists. I know there are, people like Neil deGrasse Tyson and other people like that who are trying to engage with the public on climate change and so on. Yeah, it's tough.
Do you think that there should be two groups, the scientists doing the science and then the communicators who kind of interpret the science and feed it, or should that be the scientist's job?
No, you need to train the scientists to be able to communicate. I mean, I've got nothing wrong with a really good communicator taking the science that I do and using it. That's fine.
Sure.
But I also think there is an issue with scientists not being believed and not being listened to, and but they do need to learn how to communicate and communicate better.
Sure.
We're really seeing that right now with the COVID discussions about the science of COVID, for example. Mm-hmm. And again, that's another example where who do you believe? Who do you trust? And we need some charismatic scientists there as well as in climate change. Absolutely. Yeah.
Sure. Yeah. Very cool. Well, we have officially exhausted our list of questions that we had for you. Okay. So I don't want to, and I know that we initially said, let's do like a half hour, 45-minute meeting, and now it's been an hour and 11 minutes. So
I'm sorry, I rambled on a bit.
No. I was going to say, I hope that we haven't like taken more time out of your day than you had planned for, or if you had other things, you know, that you were planning on doing at 2:11
Just
p.m.
Zoom meetings with students, but that's okay.
So it has been such a pleasure to talk with you, and it's so every time we do one of these, I learn so much. So thanks very much for sharing.
Well, lovely to talk with you all. Happy to do this again anytime.
Thank you so much.
Great. Cool. See ya. Bye.
Thank you.